Alright, today we're going to start section 12.1 and we're going to be looking at the law of sines. We're also going to be looking at finding areas of triangles and the different scenarios and when we use the law of sines and how to use the law of sines with some applications. Okay, so far we've solved right triangles. Right triangles are pretty easy. All of the trig functions relate to right triangles. Now we're going to look at oblique triangles. Well, what is an oblique triangle? An oblique triangle is just any triangle without a right angle. So one of the methods to solve oblique triangles is with the law of sines. And now there are three different scenarios in which we can use the law of sines. If we have angle, angle, side, angle, or side, side, angle. Side, side, angle is what we call the ambiguous case, or we're going to talk about that one last. But angle, angle, side, and angle, side, angle, we'll look at that first. So what is the law of sines? The law of sines gives us a ratio, or an equation to represent the ratios between a side and the sine of its angle, or of its corresponding angle. So we know side A over the sine of angle A equals side B over the sine of angle B equals side C over the sine of angle C. We can take the reciprocal of this entire equation, so the sine of angle A over the side A equals the sine of angle B over side B equals the sine of angle C over the side C. It doesn't matter which version of the law of sines you use when you're using the law of sines. However, the top one here is easier when we're solving for a side, and this one is easier when we're solving for an angle. But again, it doesn't matter which one you choose to use. Okay, so let's look at an example. So if we want to find all of the missing sides and angles of this triangle, so we know angle C is 105, side C is 20, and angle B is 40. So this is our angle, side scenario. So I want you to pause the video and use the law of sines to find the remaining sides and angle. Unpause when you're ready to check your work. Alright, so what I chose to do first here is find angle A. To do that, we just use our relationship that all of the angles in a triangle add up to 180. So I know angle A is 180 minus 40 minus 105, which is 35 degrees. You did not have to do that first. Then I chose to find side B. So I know side C is 20, angle C is 105. So 20 over the sine of 105 equals B over the sine of 40. Multiply by the sine of 40. And I get B equals 13.309 from my calculator. Make sure your calculator's in degrees, and round to at least 3 decimal places. If we had units, we would put the units on there. We don't have any units for this triangle. Then I wanted to find side A, so I used angle C and side C again. Anytime you can, you should use givens because they are not rounded numbers. There will be scenarios where you have to use values that you found, and therefore you're going to have to round. However, anytime you can avoid it, always use the given values. So I did 20 over sine of 105 equals A over sine of 35. Solve for A, and A is 11.876. Alright, now we're going to do some application problems. So a flagpole is situated on a hill that makes an angle of 18 degrees with the horizontal. How tall is the flagpole if its shadow is cast 14 meters downhill when the angle of elevation of the sun is 31 degrees? Alright, the most difficult thing about these is drawing the picture. So if we draw the picture, well, first I'm going to draw, this is the horizontal. So I have a hill on that horizontal. This is the hill. So I know the hill makes an angle of 18 degrees with the horizontal. So I know this angle here is 18 degrees. There's a flagpole on the hill. So this is the flagpole. That's the flag. And I know that the sun is casting a shadow down the hill. Therefore, the sun is up here, big ball of fire in the sky, and the shadow is going to be this distance. So this is my shadow. And I know that, let's see, the angle of elevation of the sun is 31 degrees. So this entire angle here is 31 degrees. And I know that the flagpole, the shadow is 14 meters long. So I know that the shadow is 14, and we are trying to find the height of the flagpole. So now that I've helped you draw the picture, I want you to pause the video and solve for the height of the flagpole. Unpause when you're ready to check your work. Okay, so you can see I found a lot of other angles. So for instance, if I extended the flagpole through the earth, I can create a right triangle. I know this is 72 degrees, therefore the supplement is 108 degrees. I know that this whole angle was 31 degrees, and if this part was 18, then this is 13. And if this is 108 and this is 13, I know that this is 59 degrees. So I can say h over the sine of 13 equals 14 over the sine of 59. H is 14 sine of 13 over sine of 59. H is 3.674 meters. And then we again want to always answer word problems in a sentence, so the flagpole is approximately 3.674 meters tall. Next one, we've done problems like this before with some of our other trig applications before we were using the law of sines. Back then I told you could use the law of sines for these type of problems if you remembered, but now is when I want you to use the law of sines. It makes the problem easier. So the angle of elevation at the top of a building is 21 degrees. At a point 80 feet closer, the angle of elevation at the top of the same building is 33 degrees. Approximate the height of the building. So this one's a little bit simpler for you to draw the picture, so I'm going to leave you to draw the picture, solve the problem, and then unpause the video when you're ready to check your work. Alright, so here you can see I drew my picture, and then I found a few other angles, so I knew that the supplement of 33 is 147, 180 minus 147 minus 21 is 12, and so I solved for this side here, the hypotenuse, which I called x. There are other ways in which you could have gone about this problem. This is what I chose to do. So I solved for this x using the law of sines. X over the sine of 147 equals 80 over the sine of 12. So x is 80 sine of 147 over the sine of 12, which is 209.566 feet. Now I'm using the large right triangle. So I said now I can just use right triangle trig. I don't have to continue to use the law of sines. So I said the sine of 21 equals opposite over hypotenuse, so h over 209.566, so h is 75.102 feet. Therefore the building is approximately 75.102 feet tall. Alright, the last application problem is a story of love. So two people are walking toward each other on a path through the park. The path runs east and west. A hot air balloon is directly above the path between them. One of the walkers, a female, sees the balloon when looking east at an angle of elevation of 46 degrees. The other walker, a male, sees the balloon looking west at an angle of elevation of 72 degrees. If the walkers are 55 yards apart, how far is the balloon from the male observer? Pause the video, draw a picture, solve the problem, unpause when you're ready to check your work. Okay, so here's what my picture looks like. Here's the balloon. The male, I know, is on this side of the triangle because he is looking west. The female is on this side of the triangle because she is looking east. Here's her angle of elevation. Here's his angle of elevation. Therefore, this angle has to be 62. I know the distance apart is 55 yards. I'm trying to find the distance from the male to the balloon, which is actually going to be little f, since I'm calling this angle f. So, little f over the sine of 46 equals 55 over the sine of 62. F equals 55 sine 46 over the sine of 62, which is 44.809 yards. So the balloon is 44.809 yards from the male observer. Alright, enough with those applications. So now moving on to the area of a triangle. So if I gave you this triangle here, how would we find the area of the triangle? Well, we know area of a triangle is 1/2 base times height. Alright, so if area is 1/2 base times height, well, what's the base? The base in this case is 20. So area equals 1/2 times 20 times the height. Well, what's the height? Well, if we draw in the height, so this is not a right triangle, so if I draw this in and I create this is the height, well, how can I find that? Well, I could use this supplement right here, which I know is 50, and so therefore I know the sine of 50 equals h over 62, which then tells me that h equals 62 sine of 50. So now area is 1/2 times 20 times 62 times the sine of 50, and if I type that into my calculator, I end up with 474.948. If we had units, we would put units on that. Okay, well, could I come up with that easier? Or do I have to always go through this process? Well, yeah, there is a simple solution, and that is recognizing that the sine of supplementary angles have the same value. And that should make sense because think about the unit circle. Supplementary angles are in the first and second quadrant, and the sine of those angles have the same value. For instance, the sine of 30 and the sine of 150 are the same. The sine of 45 and the sine of 135 are the same. The sine of 60 and the sine of 120 are the same. So the same is true here with the sine of 50 and the sine of 30. And so this leads us to our area formula, which tells us the area is 1/2 BC sine of A, or 1/2 AB sine of C, or 1/2 AC sine of B. And so how do we apply that to this problem? Well, we did area is going to be 1/2 times 20 times 62 times sine of 130. We did the same thing, but we did the supplement of the 130. So we had A, B, sine of C. That was our area formula. So basically the thing to point out is if you have two sides that don't correspond to the angle, then you can find the area of an oblique triangle. Okay. Last is the ambiguous case for the law of sines. So this is how the book shows the ambiguous case, how to determine if you're going to have no triangles, one right triangle, one triangle, or two triangles. I don't go by this method, but you are more than welcome to use it, so I'm just going to leave it here, and you can pause the video and look at it and try to study it and understand it if you want. Basically, it's showing you if you have some angle A and some side B, if you know the relationship between the opposite side A and the height, then you'll know how many triangles you're going to form. Well, by the time you figure that out, personally, I feel that you could have actually just solved the problem. So the method I tend to use is just go ahead and solve the problem assuming that you're going to have one solution. You'll know relatively quickly if you end up having at least one solution. If you do, then you're going to assume that you have two solutions. So that's the method I'll show you. Also, what if you're given an angle A is obtuse? Then the scenario is slightly different, and so then you're looking at if little a is less than or equal to B, then you are going to have no triangles. And if little a is greater than B, then you will have one triangle. Okay, so we are running out of time on this. I had one more example I wanted to do to show you how to do the ambiguous case, so that'll be on part 2. So here's the example. I'm going to stop this video here. We'll start it with part 2, and then we'll solve these 3 triangles.